Yep, awesome. It's recording. Let me just share my screen. Can someone confirm that they can see my screen? Because I cannot see the Teams right now.
Yep, it's all working.
Awesome. Yep. So hello, everyone. Thank you all for joining this session. So today we are just going to talk about attention is all you need. If you guys are not aware of what that term means, we will actually dive into that term. But ideally, it was the foundation behind which ChatGPT was built upon. Um, Now, a lot of you might have used ChatGPT on the high level. You might have interacted with it. You might have done some amount of research with it, or even maybe went to a couple of conferences. The problem is everywhere on the web and on the media, like everyone's kind of covering it on the high level, but no one's actually talking about the foundation on which it was actually built. So we'll try to cover the topic in today's session. Any questions which come in your mind, please leave it in the chat because this is a very complicated topic. I've tried to simplify it as much as possible to cater to the wide audience who might not be in the data capacity. But yeah, please don't refrain from asking questions. Anything which comes into mind, leave it in the chat and I'll cater to it. So let's get started. Before we start off, a brief intro of myself. So I am Sohail. I am working in the big data space inside of Telstra Purple. Currently, I'm there in the Victoria team, but I would say kind of working mostly across the country, working with people across the country. With regards to my education, I have done a Master of Data Science from Monash University. Worked in AI and cyberspace for about 5 years. So I initially started off with cybersecurity and then moved into the data science masters, which actually taught me about AI and ML and data engineering and everything data basically. So inside and outside of Telstra Purple, I've delivered engagements in AI, big data, automation, and enterprise analytics. Kind of currently doing all kind of engagements in this space as of now. A couple of certifications on which I've done in the past were Elastic and Databricks. So Elastic is a search tool, and Databricks, as you know, is a big data tool, or Apache Spark is a service. So yep, working on a couple of more, and hopefully I pass the next exam, which is there on Tuesday. All right, so before we actually dive into the presentation, let's actually kind of touch on the topics we'll try to cover today. So we'll actually get into machine learning, just understand what's machine learning, just maybe massage over it for people who already know it as well. Once we understand machine learning, we actually get into neural networks. Maybe that's the actual topic, that's the juice of the presentation, where we understand what is a neural network on high level terms, how it works, and what's the foundation behind a neural networks. Once we understand neural network, we have to cover transfer learning because it's a very critical topic to understand the next topic. So transfer learning is basically it's a continuation of neural networks. We'll touch upon it for a couple of minutes, and then we actually get into the main part, which is attention models. So attention is actually a very complex topic. So we'll kind of try to cover the overview, get into a little detail, try to cover what is necessary to actually work upon it. And then I can maybe leave a couple of links in the chat later for people who are interested to do more research. And then rather than just keeping it a talk session, we'll do a small demo wherein I'll kind of show you guys how you can actually do all this inside of Azure. All right, so kicking off with machine learning. So what is machine learning in the first place? So ideally, the diagram which you see on the right, I think that's the high level of AI, ML, deep learning, and everything else. So machine learning, as you see, is the green bubble. So it's actually a subfield of artificial intelligence, and ideally, it's nothing but mimicking the way humans learn. So humans learn from experiences, and as and when they experience new things, they actually get better. So similarly, machine learning is a mathematical way wherein we create a mathematical equation, we put it through varieties of experiences, and as and when it experiences new things, it actually learns more and more. So machine learning, the main asset of machine learning is actually data. Without data, we cannot do machine learning. I think you'll understand this better in the next slide. But actually, just having data does not mean you can actually ace in machine learning. You can ace machine learning to solve your business problem. Having good data is the primary thing. So a lot of data engineering actually goes behind getting machine learning to solve a business problem. So before we actually go to the next slide, I think you already saw that I'll be covering neural networks. So neural networks is a very small part of deep learning. It's actually blowing out of proportion in the last couple of years. The reason which we'll cover why it's kind of blowing in the last couple of years. But yeah, so AI is you can say it's the big bubble. It basically covers everything. In fact, I can say even if there are developers on the call, if you are actually just writing if-else statements, that's also somewhat related to AI. Although it's become it's kind of a battle topic whether that comes under AI or not. But yeah, AI covers a vast variety of things, and then you have machine learning, then you have deep learning, and neural networks is the most inner layer for deep learning. Or I can even say it's the heart of deep learning. So going beyond in machine learning, just before we actually get into the diagrams over there. So why machine learning? If a business asks the question why machine learning to a consultant, the reason is because there are a lot of reasons, but I think one of the best reasons which I have found is Gartner has proposed that if you implement machine learning in your business in the right fashion, with the right people, with the right processes, with the right technologies, you can actually save 15% of the operational time, which the business is spending on any day-to-day activities. And also, machine learning is not just a one-time job, like every development or every tech field. It's kind of you have to keep making it better over time. In ML terms, we actually call it retraining. So if you see the first diagram over there, you can see that traditional programming has the input as rules and data. So basically, you have data which the business has collected over the past couple of years, and then you manually code rules. And these rules and data kind of collate into that traditional programming umbrella, and they give out answers. Now, machine learning is nothing but it's a slight tweak over there. So instead of providing it rules and data, you're actually providing it answers and data, and then you're telling the machine learning model to actually figure out the rules. Let me just check if this works here. So, yep, it's working. So basically, in usually in business problems, when you encounter data and when you actually talk to the stakeholders and try to figure out the rules, you actually see that the rules are very complicated. So it usually won't be a simple if or else. It's actually going to be maybe tens of thousands of if or else. So actually manually coding that rules, it's going to be it's going to be a very big task for a business, unless and until there are certain use cases where you have to go that way. But yeah, manually kind of coding that rules, it becomes a total pain for the developers, for the people who are trying to implement it, for the people who are trying to understand it, or for the people who are trying to use it and maintain it as well. So usually these businesses have data in which you have patterns. So rather than actually manually coding the rules, you actually give it the data and the answers which have been collected over the past couple of years. You give it to machine learning models, and then it figures out the patterns which are actually the rules. And then you can actually deploy the rules which act as, which basically you can just give it the data and then it spits out the answers based on the rules. So that's the basic of machine learning. Now let's get into the actual thing, which is deep learning or neural networks. So what is neural network in the first place? So neural network is, it's really hard to define neural networks. There's a lot of definitions in different areas, but I think neural network can just, on a very high level, you can just think of it as a neuron. So the brain actually has neurons, which are actually communicating with each other. So neural network is mimicking that network, in which the brain actually functions. The only problem is to actually build the network, you need a lot of data, which we'll actually get into. So yeah, let's maybe take an example to make it easier. So you can actually see the graph over here. The graph actually shows us the house prices. Imagine we are trying to create something which actually, wherein we are actually trying to predict the house prices. The x-axis is the size of the house, and the y-axis is the price. And say this is 0. So over here, based on the size of the house, you can see that the price actually increases. Now, if you want to fit a mathematical formula to this, you can easily see that a linear regression is the best way to actually fit on this kind of graph, which actually shows that as the size of the house increases, the price is actually linearly increasing. Now, the problem is there is no house which actually goes for less than zero. So I'm considering this maybe is something like an ancestral property or something like that, but nothing grows less than zero. So you have to basically make everything before the zero as zero, and then everything increases linearly. So over here, you can actually see that this function is actually called a ReLU function in math. It's a very famous function in math and in neural networks. Um, so similarly, you can see that usually for any problems in the world, if you actually plot it on a dimensional graph, you can actually try to fit a function on it. And function, as everyone knows, is the basic of math, where you have an input and an output. Um, so basically, if we actually fit the ReLU function to this, we can actually consider that function as a neuron. So imagine this is f, the function, the ReLU function. So the neuron, in this case, we have the neuron, wherein it's just a ReLU function, which is a linear regression, and everything before zero becomes a zero. You input the size of the house, and then it spits out the price. And this is neuron. On a very high level, you can imagine a neuron functions like this. So basically, it's nothing but you have an input, x, and you have an output, y. So y is basically mapped with the help of a function, and the function is just taking the input and it's actually creating an output. So that's one single neuron. So when you have neurons like this, you can actually, so I can say neuron is like one Lego brick. So when you actually stack neurons on top of each other, and when you actually take hundreds of parameters inside a specific business problem, you can actually create a network. And these neurons which are stacked on top of each other with maybe multiple layers is actually called a neural network. So let's actually build a neural network for predicting house prices. So say you have one neuron, which actually takes the size of the house and the number of bedrooms. So the size basically indicates the land size or the unit size, and the number of bedrooms is how many bedrooms are there inside. Um, and that, say, for example, gives out an output called family size. So we are trying to predict the family size based on the size of the house and the number of bedrooms. Say you have another neuron, which takes in the input as zip code. And based on the zip code, it actually tries to predict or it actually tries to calculate the walkability to the nearest station. So how near is your tram station or train station and stuff like that. And say we have a third neuron, which actually takes in the input of zip code and the wealth of the society. So how wealthy are the people living in that specific neighborhood? And based on that, say, for example, you're trying to predict the school quality, which is what's the rank of the school, because the zip code and the wealth actually indicates whether the schools are on top or not. For some reason, that's how data is working in most of the cities, at least. So you input the family size, you input the walkability, you input the school quality to another neuron, and that basically predicts your price. So ideally, all you're doing is nothing but you're stacking a couple of neurons on top of each other. You're taking specific input parameters. And then once you given specific input parameters, it tries to predict one specific output parameter. And that specific output parameter is just, again, fed into another set of neurons and so and so. So ideally, if you actually see the neural network as a user perspective, when we are actually trying to build a neural network, we actually see it from an input and an output perspective. And then I can say the number of layers which are inside the neural networks. This is also something which we usually look at. So we can actually specify if we want three layers or four layers and stuff like that. So in this case, we have only two layers. Usually, more the data, more the number of layers, and so on. Now the problem is we cannot actually predict what happens in between. This is really hard for this example, it's pretty easy, but as and when the business problem kind of gets complicated, it's really hard to predict what happens in between basically the communication which are happening in between two different neurons. So when we are actually try to create a neural network, This is what we are focused on. So we just take the set of inputs. In this case, we take the size, the number of bedrooms, the zip code, and wealth. These are 4 different inputs. We just throw it at the neural network. We do not really care about what happens. So we, like I mentioned, so these things we do not really want it, because it's really hard to kind of specify what's happening in between. I think the only thing we can kind of focus on is something called weights. If you don't know, this is not a problem. I'll maybe send a blog which you can read to make it clearer. But yeah, we can just specify the weights. We just throw in a couple of inputs. The neural network tries to figure out what happens in between, and then it just tries to predict the output. So this is the understanding of a neural network on a very high level. So now the question arises is, why do we actually need deep learning? The easiest way to explain this is using this graph. So this graph was actually created by a person named Andrew Ng, who's the founder of deeplearning.ai. And this was the easiest way to explain why deep learning is required in today's generation. So over the past 20 years, data is actually blown out of proportion. So companies have been collecting data for the last decade, but over the past 20 years, because of digitization of almost everything, companies have collected a lot of data. If we actually take in machine learning, and this is actually machine learning, so just traditional normal machine learning algorithms, something like SVM or logistic regression or anything of that sort, you can see that as and when the data increases, so this is the amount of data, or amount of data, if you guys are not clear, is just the number of rows, which is specified as n or x in some cases. So as and when the amount of data is actually increasing, and we are talking about labeled data over here, we can see that the traditional machine learning algorithm, actually the performance of it decreases after a certain point. So say, for example, you have some data which is 1 gigabyte, the machine learning algorithm performs good. You have something which is, say, 1 terabyte, a file, a CSV or a Parquet file of 1 terabyte. The machine learning algorithm performs a little better, not really good, comparing the amount of data which is scaled exponentially. And say if we have something like 1 petabyte, the performance is almost the same in that case. So basically, as and when the amount of data is increasing, traditional machine learning algorithms do not perform very well. Or you can say that they actually stagnate after a certain point. Now, if we take a small neural network, and what do I mean by small, medium, and large, is nothing but the number of layers in between. So in this case, there are only 2 layers. So yeah, we are talking about that in small, medium, large. So if we take a small neural network with maybe something with less than 10 layers or something like that, we can see that after a certain point, that stagnates as well. So I think that's stagnating after 1 TB. So after the data set size basically scales up after a terabyte, it does not perform very well. It kind of stagnates after that point. And if you take a medium neural network, that maybe stagnates after something like 10 terabytes. And the large neural network actually starts stagnating about at the 1 petabyte scale. And these are just examples. Live environments might behave differently, but yeah, these are just examples for just making it easier to understand. So the reason why deep learning is kind of blowing out of proportion in recent days is because of this this line. So over the last, I would say, over the last 3 to 5 years, the scale in which data which is being produced and which is being cleansed, and all the tools which are there to actually make the data in better shape and format and size is actually becoming better and better. So basically, there's big scale in data, there's big scale in computation, and there's big scale in algorithms, and all 3 have favored deep learning. And for deep learning to actually work very well, you actually need a large neural network, which means you need multiple hidden layers inside the neural network, and you actually need very big data sets. So because in the last couple of years, we do have access to very big data sets and big neural networks. So that has made it easier for us to train bigger neural networks and get that highest performance, kind of peak that performance out. So going ahead, let's actually just try to cover the types of neural networks. There are actually multiple types of neural networks, but to make it easier, we kind of are covering the three main types. So standard neural networks is what we were talking about. It's just a couple of neurons which are placed horizontally with each other, and then you have um, different layers in between to actually make the predictions. So a standard neural network is usually it functions very well with text data and with structured data sets. So if your data has structure, if it has a fixed number of rows and columns, which you can define initially, then a standard neural network is very good with handling that type of data set. The next you have convolutional neural networks. Now this is really good with, so this basically tries to take the data and it tries to uh, plot that in multiple dimensions. And you have neurons in multiple dimensions which are working with each other to actually make the predictions. So convolutional neural networks, it usually works really well with something like image recognition or image labeling. So anything with image, basically a convolutional neural network works really well. And then you have the last step, which is what we'll be covering in today's topic. So the recurrent neural network. So the RNN is basically a sequential of neurons which are placed on top of each other. It has something called feedback, which we'll be covering. So this is really good with handling sequential data, something like speech recognition or language translation. Or say, for example, autonomous driving, the Teslas of today, and natural language processing. So usually in language, it works really well because language actually has a certain sequence which we follow to communicate with each other. So these are the three kind of high-level types of neural network. And diving further, we'll actually try to get into transfer learning. Like I mentioned, if you have any questions, please leave them in the chat, and we can have a discussion at the end of this presentation. So what is transfer learning in the first case? Um, so as human beings, we actually take knowledge from one task and we try to apply it in another task. So say, for example, if you want to ride a motorbike, or if you want to learn a motorbike, you actually go and maybe buy a motorbike, and it becomes a little easier if you have actually learned how to drive a bicycle when you were young. Um, so say, for example, when you were young, driving a bicycle, it took maybe 2 or 3 years. Um, and Now you take a motorbike. It's definitely not going to take 2 or 3 years. Maybe it's going to take like 2 or 3 weeks for you to learn, because you're actually applying the knowledge which you have learned, or from the experience which you have had of driving a bicycle, and you're kind of taking that to actually learn and drive a bike, because a lot of things are kind of common. So say, for example, balancing the bike, or say tilting and making turns and stuff like that. So that kind of becomes common. So you can actually take knowledge from that and apply it to this. And that's basically the idea of transfer learning. So similar to how the brain works, we have neural networks which are ideally mimicking a human brain. So what it does is it takes knowledge from one task and it tries to apply it to another task and become better at it. So let's actually take an example uh, rather than. So say, for example, you have a neural network. So in this case, you have 1, 2, 3, 4. So you have around 7 layers. You have different number of neurons in each layer, and they are basically trying to perform some sort of prediction. So say, for example, just to make it easier, say this was an image recognition neural network. So in this case, you have a data set with all images, and you have a classification to say, for example, you're trying to classify an animal. So it actually tells you which animal that image is, whether it's a dog, whether it's a cat, whether it's a bird and stuff like that. And usually for image recognition of animals, something which is very easy to find, the data is very easy to find for these kind of problem statements. Say, for example, you have around 1 GB of data for this use case. So you have millions of rows of samples to train upon. And say you actually train a neural network with this data, and you get this neural network, which is a ready neural network for us. Now, what I want to do is say we have a use case where we actually need to do radiology diagnosis, which is in medicine. So it's something like taking X-rays and uh, trying to predict something like something in the medical field. Um, Apologies for my handwriting, but and say you have a prediction of something in the medical field, for example. And definitely it's really hard to get this kind of data. So say you don't have 1 gigabyte of data, you have 1 megabyte of data, which is about 1,000 rows or 10,000 rows, depending on which file type you're using. So because you have lesser data in radiology diagnosis compared to the image recognition, so rather than actually creating a neural network from scratch for this data, what you do is you actually take this neural network, you scrap out the last layers of the neural network, and then you make a couple of layers in between, and these layers are actually trained with the help of the radiology data in that case. So the idea of transfer learning is this. So rather than actually training the complete network, you actually scrap out the last couple of layers. You take the data set which you are transferring the knowledge to, and you create a last layers. You maybe give it a couple of things called weights, and you also give it something called bias. And basically, you are using now you're using this model. So after scrapping out this and creating this new layers in the last, you can actually use this neural network to predict a radiology diagnosis. So you can use it in the medical field. So this is the idea of transfer learning. If you guys are confused, I can even maybe say, for example, if you say, for example, you have speech recognition data. Uh, so something like Google, which has it has maybe speech recognition data for about 10,000 hours, let's say, and you're trying to predict. Say, for example, you want to train, you want to kind of train a neural network with your set of data, which is wake word detection. So something like if you are telling OK Google or OK Alexa, the device has to kind of react, or it has to function at that point of time. Now, the problem is wake word detection. You don't really have a lot of data. It's really hard to get 10,000 hours of data for wake word detection. So basically, the same way, you scrap out the last couple of layers. You give the wake word detection uh, data, which is say 1 hour, to the last layers. You create the last couple of layers with some certain amount of bias and weights, and you get a new neural network, which you can use for your specific use case. Now, in technical terms, when you are actually training a neural network the first time from scratch with a lot of data, so that is actually called as pre-training. And the model which is actually created, so in this case, this is the model. We don't have, so this is the actual model which is created based out of the big data which you have to make it simpler, say image recognition or speech recognition. So these models are called pre-trained models. And once you have a smaller subset of data to which you're transferring the knowledge to, you scrap out the last couple of layers, you create new layers in the end. So that process is called as fine tuning. So these are just the technical lingos in neural network which are used. So you have pre-training, you have pre-trained models, which are the actual neural network which is created. And then you have fine tuning, which is taking a smaller subset of data and performing the transfer learning job to make a new neural network, which actually can cater to your needs. The reason why transfer learning is done is because of a lot of reasons. One reason is because, say, for example, you don't have equal amount of data. Something like radiology diagnosis, it's really hard to find data in that case. And when you want to do the job faster, so rather than sitting and creating the entire neural network, which is going to eat a lot of compute time and money, so pre-training makes it transfer learning makes it a lot of it makes it a lot easier, because you take an existing model, you're saving your compute, you're saving your time, getting better accuracy, because it's already a bigger neural network you're dealing with. So just to maybe cover this again, when does transfer learning make sense? Say, for example, you have a task A and you're transferring knowledge to task B. So if the task A and task B has the same input n, in that case, it actually makes sense. So say, for example, task A is speech recognition, and task B is wake word detection, which is OK Google, OK Alexa, and stuff like that. So it makes sense. But if task A is say image recognition and task B is speech recognition, or say wake word detection, it cannot make sense because the inputs are totally different in this case. So your input data has to be the same. And say in you have a lot more data in task A than in task B. So like I mentioned in the previous slide, you have say gigabytes of data to actually train your neural network to create a new neural network in task A. But then in task B, it's really hard to curate data, or it's really hard to find data for those kind of business problems. So in that case, transfer learning actually makes sense. And also the low level features of A should be kind of helpful in helping B. So basically, so ideally what this means is the low level features which are used for neural networks should actually make sense in both the business problems. So you can't really have features which are different. And features just mean columns in machine learning. It does mean a lot different things in different business scenarios, but yep, ideally you have to have the same set of data, or it has to be very similar. You can't keep it very different and try to perform transfer learning, else you're going to get really bad results in that case. All right, so let's get into the main topic for today, or I would say the topic of this entire presentation is attention is all you need. So just to cover what is recurrent neural networks, you saw that recurrent neural networks is helpful for sequential type of data. And like I mentioned that time, it's really helpful in the case of natural language processing. The reason is because when we are actually communicating with each other, we talk in a certain sequential manner. There's certain amount of grammar, there's certain amount of sequence associated with the way we communicate. And that makes a recurrent neural network a very good fit for this kind of business problem. So say, for example, you have an example, you have a statement, an English statement, which you're trying to transfer into a different language. So in this case, you have a couple of words, and then you have a translation for each word, and that actually is being translated into a different language. So that's ideally what RNN works. So you have the word, say, transformers are great, and this is being translated into German or some other language, for example. So ideally, what it does is your RNN takes each word as an input. It performs a translation for that word, and then it just spits that output out. Now, the problem with this is when you are actually translating an entire English sentence, there are a lot of components which we'll have to look into. So say, for example, if the sentence is very long, the grammar in different languages can be actually different. So if you take each word and translate it to a specific language and just give it as an output, the person, say, for example, you take an English statement, you translate it into German, for example, and you call maybe a person who's from Germany and you tell him to read it. And now once he's reading the German translation, he's not basically he's not going to understand it, because in that case you've just taken word to word and translated it, and it loses a lot of characteristics or features which are actually there in the sentence. So a lot of I would say meaning which the sentence is holding, that actually is lost. So the problem where recurrent neural networks faced is, so say you have the x-axis as sentence length, and say you have the y-axis as your predictability score. So the problem in neural network, in recurrent neural networks were, when your sentence length is actually short, the RNN performs really well. So this is high value. So basically your prediction score is really high. So it's performing really well. But as and when the sentence were becoming longer and longer, say when you're inputting paragraphs, or basically a person is talking for, say, for example, I have this presentation which is running for an hour. You take this entire uh, uh, text which is there, which I've basically talked, you give it to a recurrent neural network and tell it maybe translate it to German or French or any other language for that matter. It's going to perform really well because there's a lot of meaning when I'm talking word after word. And that gets lost in the translation. So as and when the sentence length is actually increasing, so RNN basically it loses its performance. So it won't be fit for purpose in that use cases. So even though RNN it deals basically it takes sequential data really well. It does have a feedback loop. So feedback loop is just nothing but taking the input of the previous word and giving it as a feedback. So even though it has these characteristics, but performing on big sentences or performing on certain positional things, which we'll talk about later, so that it actually fails. So that's when Google in 2017, a couple of researchers in Google came with a research paper, which is named as Attention is All You Need. So a couple of people from Google gave out this research paper in about November of 2017. And I think everyone in the neural network industry, in the deep learning, machine learning, any space, any data space, they are going to say this paper actually changed the game for in the field of data science and in the field of neural networks. So the fundamental proposal for this paper was actually not very hard to understand. It was pretty. It's a very complicated research paper, but it's just covering three basic points, which were positional encoding, multi-head attention, and self-attention. So positional encoding is just basically this is it just considers the position of a word in each sentence. So it basically it takes in a sentence. So say for example, rather than let me actually think of a sentence. Yep. So say for example, you have a sentence. So a person, say for example, his name is A, and you have a sentence: A's dog looks like a pit bull. And even though the grammar might not be correct, so these are two sentences. The first sentence is, say we have a person A who has a dog, and the dog basically looks like a pit bull. So A's dog looks like a pit bull. Now we're just changing the position of the word dog. So A looks like a pit bull dog. Now this actually flips the sentence totally. It's making two different meanings altogether. So this is positional encoding. So it based on the position of each word, you are actually getting different meanings. And then you have something called self-attention. Self-attention is nothing but it's taking each word in a sentence, each ith word in a sentence, and it's looking at its own relevance with regards to other words which are occurring in that given sentence. So basically, if you have each of a word, you take the relevance of that word with regards to the complete sentence. Now, one thing to understand is computers usually do not understand natural language. They can't really understand words and text in this format. So everything is actually vectorized. So words are usually plotted in a dimension, um, and they are basically, say for example, you have dog over here and you have cat. And say we have another thing over here which has the word look and like. So when you are actually plotting words in a two-dimensional or a three-dimensional matrix, you're actually taking all the words which are nearer to each other, and you are associating certain amount of numbers to them. You're associating a couple of numbers to them, or a couple of vectors. So ideally, like I said, computers they cannot understand um, words. So they actually vectorize it, or they perform something called embedding, and this can be done with the help of pre-trained models as well. And these embeddings basically look at the position, and it looks at the self-attention. Which and self-attention just means how relevant it is that one specific set of numbers with regards to other set of numbers in that statement. Now the problem is you are actually doing that for each word. So say for example, I take in this word, I do the self-attention for this with regards to other word. I take in this word, I do the self-attention to it with regards to other words. Now the problem is when you're actually focusing on this word, which is just a set of vectors, say it is 2, 3, 7, 1. When you are actually performing the self-attention mechanism, um, the word gives more attention to itself than other words in the statement. Basically, if you got confused, it's nothing but say you're performing self-attention process for this specific word. It gives more attention to its own self, its own presence, rather than other words presence in that given sentence. So that usually creates bias in the model, and it hits the performance. So what there's a mechanism called multi-head attention, which is just vectorizing all the words or vectorizing that word multiple times with regards to different positions, and then taking kind of a mean, or maybe just kind of narrowing it down to one specific, or taking the average of basically all the vectors. So that's the concept of multi-head attention. So ideally, this paper focused on positional encoding, which is the position of the words. If this thing was confusing, not a problem. So on a very high level, this actually takes into consideration the positions of the words. This takes into consideration the self-attention, or basically how relevant is that specific ith word with regards to other words which are occurring in that English sentence. And then it takes a multi-head attention, which is an average of all the vectors, just to normalize it and um, keep the numbers and the performance pretty high. So this is the transformer model architecture. Now this one itself can actually take about 1 hour to explain. So I'm not really going to get into the deep depth of it, but this was what Google had proposed. So like we have seen positional encoding, so that's actually done by this layer. The transformer architecture, basically it's a encoder decoder layer. So on the left, you actually have an encoder, and on the right, you actually have a decoder. And this basically helps in something like translation, um, or performing any other things with natural language. And then you have multi-head attention, which I just mentioned. So that's actually taken care by, sorry. So that's basically taken care by this block. You have a normalization at the end, which I just mentioned. It's just going to take an average and keep things normal. Uh, so it's basically a mathematical way to take do normalization. It's actually called normalization. And then you have a feed-forward network, which actually performs more normalization on the data. So this was what was proposed by Google. Um, and once you actually have the inputs which are which go out, you actually give a feedback as outputs to the output embedding. And again, the output embedding is just performing embedding, which is taking the words which are predicted for each given statement, and it's mapping that in space to a vector. And then like the input layer, you actually have the positional encoding, which actually takes into case the position of the words. You have the multi-head attention, which is performing the average, or kind of taking the number of vectors with regards to different words in the sentence and kind of averaging that out. And then you have the feed forward layer, which is just again normalization. And then you have the linear and the softmax. So this is again normalization and probability. So softmax layer is just doing the probability distribution of. So say, for example, you predict a word to a specific, say you're converting English to French. So you take a word, you convert that word to French. Now you have the word, you have the position, you have the vector. So probability basically, you get, because you get a set of output. So probability takes the highest probable output, and it gives you that specific output. So if this was kind of confusing, I think because it's really hard to cover this in 10 minutes. Uh, so maybe we can have another session on this where we actually get into the detail of what's an attention network or attention models in specific. But on a very high level, ChatGPT actually used this technique. And all we need to know as users is you actually don't need to know the exact understanding of attention model, or what's happening in the vectors, or what was the word converted to which number and stuff like that. You actually don't need to go into the details as users. You can actually take common data and try to train these attention models. So ChatGPT or OpenAI, the company behind ChatGPT, they have done the same thing. They took open data which was available. It was basically the World Wide Web data available from places like Common Crawl, from Open Web Text 2. They had heavy compute, and they have a lot of data which are from sources like this. This is not really documented anywhere, so I'm not sure what other sources they've used, but I'm pretty sure these were the two common sources which they have used. They have trained their neural networks or their attention models using all this data, and they have obtained something. They have basically obtained the pre-trained model um, in this case. So they have got the neural network. So when you are actually communicating to ChatGPT, all you're doing is you are asking a question to that pre-trained model. And once you ask a specific question, it performs a certain amount of computation and gives you an answer. So that's the entire understanding of how ChatGPT is working. So you can imagine it's just a neural network trained on tons of data with huge compute involved. And once the training was done, it was completed. There was a neural network which was ready, and you are just communicating with that specific neural network. Now, going back to transfer learning. So transfer learning, we covered that we have two major technical terms, which are pre-trained model. And these are the actual models. And you have something called fine tuning, which is you're taking a specific network and you're making it fit for your use case. So can you do it with OpenAI? The answer is yes. So imagine this is actually the ChatGPT model which was given to us. And you have certain amount of data in your business. So you basically just remove the last two layers. You add a couple of layers using your business data. And now this specific ChatGPT model is working as per your business case. So this is the whole idea of OpenAI model as a service. So ideally, they are giving it to you as a service. You pay them a nominal fees for actually using the models. Say you have corporate data, which you are giving it to the model. Now this, once you actually give it the corporate data, you are performing a transfer learning, which is you're taking their network and you're transferring that knowledge to your specific business problem. You get the model, which is catered to an organization, which you can call as the fine-tuned model, which we already discussed what it is in transfer learning. And then the models can be consumed by processor. It can be consumed by APIs, by business, by human beings, by users, by customers. Basically, anyone can actually consume this model because it's actually fit for that specific business. And once the model is actually being consumed, there is more data which is being created. So that actually again goes in, it's actually again stored in data warehouses or lake houses inside the corporate world, which they again can retrain the OpenAI models to make it better and better. So this, I think, the whole cycle can actually be used by any businesses to solve a certain business problem or to make things better in their organization. So that being said, I think we can do a quick demo. So in this demo, we'll just go through how basically what OpenAI is on Azure, how to access it, and how to kind of train your own models using your own set of data. So firstly, to actually access this, you can just Google the term Microsoft Access to OpenAI. And once you do that, it gives you a website, which actually might go to the actual OpenAI link, when you actually have a link to actually fill a form. And this is the form. So you have to fill this form. Basically, you have to name your organization and basically tell what's the purpose of usage. If you just mention training and self-learning, they give you access. It takes about 10 business days. Once they actually give you access, you have you can just go to the portal. You can use your subscription, the kind of the $70 subscription fees which you get month to month, and then inside a specific resource group, you can just type in OpenAI and create a specific. You can just create the resource. So in this case, we have already created a resource. So once you actually create a resource, you get this link. And when you actually click on explore, it takes you to the OpenAI Studio. So the OpenAI Studio is just, it's a no-code experience to actually use these models to train your own models for your own business use case. The main, I would say that to start off, the best place to go is models. And when you actually go to the base model, so these are all the pre-trained models which OpenAI has trained and kept for us to use. So we can actually just take these models and give it our own set of data, and we get our own set of fine-tuned models. Or you can even take these models and deploy it and start learning as well. So you can do it either way. So ideally, OpenAI has four set of models. It's Ada, Babbage, Curie, and DaVinci. So you can just consider it as ABCD. Ada is a smaller neural network, and the thing with D, which is DaVinci, that's a bigger neural network. So as in when your neural network size increases, your performance increases and everything increases, and of course cost also does increase in that case. So you can select a certain model, you can deploy it directly, I cannot deploy this because I've already deployed it, but yep, you can just deploy it directly. The other option is you can actually create a custom model. You can select which type of model you want. Like I mentioned, this is a small neural network, a little bigger, and this is one of the biggest. And after this, there's something called DaVinci, which is not there for some reason. And again, this is there in, it's still very basic. There's a lot of improvements are coming on the way as per Microsoft announcement. So once you actually do that, you can deploy it. That's one option. Um, or when you actually want to create a custom model, you select the type of model which you want, or you select the type of neural network. Once you actually do that, you go to the training data wherein you give it the data set to which you need to train on. And that's basically the process of performing fine tuning. And then you give it a validation data set to make sure validation is perfect. And then there are a couple of advanced options. This is for hyperparameter optimization to give it certain parameters for it to follow. And then you have the review stages. So in this case, I've created a couple of models. I've taken the ADA model in this case, and let me just, yep. And I have deployed one of the models. So when you actually click on the model, it gives you basic parameters as to how the model is performing on a day-to-day basis. You can actually even download these files and use it for analysis purpose. And once we actually kind of take a pre-trained model and fine-tune it for our business use case, uh, you have a model which is ready to use. Now, once it's ready to use, you can actually deploy it. So I've just selected this and I click on deploy. It goes to the deployments. I'm not doing it now because this takes around half an hour. So feel free to try it. And once you deploy it, it asks for a deployment name and it's ready to use. So if you want to actually try out this model, you can just open it in the playground and you can start giving it inputs. So just to go a brief, I really hate to kind of take people through code in presentations. But ideally, this is just basically the business problem behind this model is you have a tweet and it has to predict whether that tweet is is it baseball or is it hockey or which sport is the tweet referring to. So that's a simple business problem. Um, the problem is the classification variable, which is the name of the sports. There are too many sports over there, so there are hundreds of sports. And now, usually, when like 2 years before, if you're trying to solve a problem like this, any ML engineer gets confused whether you have to get this into a classification bucket or whether you have to get into a regression bucket. So uh, now I think it's easier with things like OpenAI. Um, so once you actually do it, you can give it certain parameters as you like. So these are just giving a certain number of parameters. Um, And once you do generate, it's actually taking the input, it's hitting into that specific model which we actually created, Twitter classified sports. So that's the actual deployment, and it's giving the sport name. If you actually want to even try out, so say for example, you're not well versed with neural networks and fine tuning and stuff like that, but you just want to get a glimpse of it. There are also a couple of examples which they have given to make it easier. So say we want to create natural language to SQL. So this actually needs the code DaVinci too. And in some cases, it does not deploy. That's because they have a lot of restrictions in place because a lot of people are actually trying this out. But you can actually try to deploy this resource in a different group, in a different region and try it again. But all you have to do is go to the examples. It generates a certain example. It tells you which model it has to be deployed, basically to give out the predictions. And then you can just give it an input. Or change the input and hit on generate, and it generates something. In this case, I am taking this input and I am giving it to my model. So it's going to give out garbage results because it's not trained for this business problem in this use case. And yep, it's taking some more time. And then you have the chat playground. Um, so this is it's so this basically is using the 3.5 version, the GPT 3.5 version, and this is pretty fast because it's already trained and it's kept on the cloud for us to use. So we can actually give it inputs. So say for example you have a hiking recommendation. Now let me just copy this and paste this. So basically over here it's trying to tell that you are hiking. Basically, you're trying to tell the model what job it has to do. So in this case, you're trying to tell that you're a hiking assistant. Your name is so and so. So you have to basically ask the person where they are located and what interests they are looking for in their hiking experience, and it gives you a recommendation. Now, the thing with Microsoft is working on is they are going to add a new feature over here, which is to do custom deployments with this model. So basically, if you have your own set of business data, or say you are a tech support or you're a call center or something like that, you have your own set of data, you can actually take the data, train this model, and it start behaving or start mimicking the way you're actually training it. So in this case, for example, just one prompt, I've just told that, basically I've just told the model that you are a hiking assistant. This is what you have to do. So imagine if you have like terabytes of data, kind of telling the model that if this is the input, this is the output. So you can imagine the kind of performance it's going to give. So on a high level, this is Azure OpenAI. This is I would say this is very high coverage of it. It's still going to get a lot better, but I think it's a good time to start playing around with this, because once it actually gets better, it's going to blow up with a lot of features, and then yep, we can start learning the features and using it for our own business use case. If you are confused about how to actually train your data, you can go to the documentation. You can, I think, go on quick starts, and you can go on how to prepare data set. So this basically tells you, if you have a certain data set, how you have to kind of prepare it for the model to understand. So this has something called a prompt completion mechanism, wherein you give it a prompt and it does a completion. So yeah, it also goes through how you can do it using the OpenAI plugins for different languages. So yeah, this is, I think, the fastest demo I could have done. Uh, Yep. So I think now the main part is questions. Any questions? Let me open the chat in the meantime. So basically, it's, yep, anyone can unmute and ask questions, or they can leave the chat, leave it in the chat. I'm not seeing anything in the chat. Any questions, anyone?
I wasn't here from the beginning of this session, but maybe you already discussed that. A bit regarding that preparing the model that you also mentioned regarding that documentation. So should be, if I want to train a model, should I give that model based on the question answers, or it could be any type of text that it can infer the detailed information from that text?
Yeah. So ideally, um, ideally, I think these models are actually well versed with natural language. So if your text has natural language or natural sort of communication, so for example, in the demo, you could see that I actually take a tweet, and then it tries to classify which sport that specific tweet is talking about. So if your data has natural language in it, you can prepare the data set using the documentation which is given by Microsoft. Based on the kind of data you have, it might be a little harder for your specific use case. So you might have to spend a lot of time on the engineering aspect. But yeah, once your data is ready, you have the prompt, you have the completion, you have it in a JSON file, you're good to go. Just upload it to the model, throw it. Whatever I've discussed is just the foundation. So just understanding the foundation makes it a little easier to, it gives us an understanding of what's happening behind the scenes. But yeah, you basically don't have to worry about all that. Just throw the data at the model, and it's going to work as per your requirement.
Great, thank you.
Any other questions? All right, I think if not, we are right on time. Uh, it was a little hard to cover this topic in an hour, but I tried to squeeze it in and try to talk a little faster. So if if you guys were basically missed anything, you can go to the recording and slow down the speed and try to listen. But yeah, if you guys are interested to actually know what is attention models, you can definitely reach out. Maybe I can arrange another session and keep an hour just to discuss of what attention model is. But And yep, maybe start experimenting with OpenAI, try playing around with it, and hopefully one day I think all consultants will be using it for our own business problems for our customers.
Thanks, Sahil.
Thank you.
All right. Yep. Thank you, everyone.
Yeah, bye.
Thank you.
Bye bye. Thank you.